to Pump Video Academy Online, module number 9. I'm Len Miller. Last module, Pump Video Academy number 8, dealt with power transients. Fluid transients that happen in a power plant when there's a load rejection, generator trips, or some other faulty instrumentation or sudden load reduction happens. We discussed it as shown in the diagram, which is simplified view of the power plant, that the boiler pit pump feeding the boiler, which boils water into steam, and steam goes to a steam turbine, generate electricity, and then exhaust to a low pressure into a condenser to condense back to water. And then on the way back to the suction of the boiler pit pump, it goes through the Deaerator for the purpose of removing air. And during this process, the Deaerator gets pegging steam, so-called pegging steam, extracted from the turbine, usually intermediate or low pressure side of the turbine. That steam heats up the water, keeps it in saturation under the pressure, and removes the air. At the same time, condensate that is coming to the DA is a colder side. So steam is hot, condensate water is cold. Overall, everything is in balance. The DA usually roughly 2/3 full or so it's mostly liquid water with a steam fraction, small fraction. Usually it's right at saturation or a couple of degrees above saturation in a subcooled region. So everything is going nice and smooth, I think, until something happens. And the load rejection causes sudden interruption of the steam. Condensate pump still continues, unfortunately, in this example, deliver cold water to the DA, it flashes, and why it happens, we'll show in a minute, from thermodynamics. The flashed water and reduced pressure cause insufficient suction pressure to the boiler pit pump, essentially lacking NPSH available, which becomes now less than required, and boiler pit pump goes to distress. It vibrates, shuts down on PSH, so bad things happen to the pump. Thermodynamically speaking, we have temperature versus unit volume, cubic feet per pound, and this is temperature in Fahrenheit. And then the liquid region is to the left, vapor to the right. Under the dome, there's a two-phase region. So when the pressure and temperature drop from the saturated point A at a constant volume, assuming the volume of the DA is constant, and that also can be questioned slightly, but for now, for simplicity, we'll assume it's a constant volume. So the flashing causes A going A to B, and B have a small fraction, the mass fraction, X. It's called in thermodynamics. X fraction. In mass, it's a small fraction. Most of it is liquid. But in volume, it's a very substantial amount of volume. If that volume gets sucked into the DA toward the suction head up to the pump, problem. Now, what happens, that is a DH. What happens if we now have not a single pump, but let's say two pumps? Let's add another pump. Another line, and another pump, which is also connected to the discharge to the boiler. And let us say this pump was running, two pumps were running simultaneously, and pump number, call it 1, and this is 2, going through the initial cycle of the load rejection, the event at the plant, and this pump shuts off. So the fluid collected as a suction handle, which could be 100 feet in length, or the height to the DA, that fluid is hot. The fluid in the suction header leading to the pump number 2, which is still operational at this moment, keeps getting cooler as the A receives colder water. That colder water gets cooler and keeps on pumping to the boiler, to pump number 2. That pump runs just fine because saturations at a lower pressure and temperature, but still in saturation condition, remains at the DA. No problem. But the pump number 1, non-running pump, now experiencing lower pressure on top of the surface of the DA, but higher temperature. If this pipe is well insulated, it retains, imagine 100 feet of pipe, 16, 18 inches diameter, it has a lot of water, maybe 1,000 gallons of water or so. All this water now is at lower pressure, and if you go low enough, it can become low enough below vapor pressure at that elevation temperature. If this water gets below vapor pressure, it will flash. But flashing is tricky. Normally, we have an open container, and we reduce pressure in the container, the fluid will flush, but if the container is constant volume, it has no place to go. If we have a piston on top of the container, and the pressure is reduced, then it's a constant pressure situation where the tip of the can will lift up and will reach the greater volume to accommodate extending vapor. Well, in our case, is it a constant volume or constant pressure? We can think about a deaerator and a portion of the pipes as so-called control volume, which is essentially constant volume. We can theorize that it is constant volume. There are connections. This, of course, closed for the steam, but there's a connection open to condensate pumps and the boiler pump. But the vapor cannot readily go through them. It has to first get to the water that connects the pumps. As the vapor bubbles up, expanding, it can now encounter. It's encountering a lower temperature zone in the DA and in the suction head of the second pump. When the vapor gets to a colder region, it is transforming back into the liquid. It takes a fraction of a second, milliseconds. The question now remains, what will happen with the flashing of this pipe? Will this pipe, the first pipe, affect what happens in the second pipe and therefore affect the boiler pump or not? So we're now going to look in two scenarios. The first scenario we reviewed on module number 8, PVA-9, which was published in Pumps and Systems magazine in March. And in April 2015, we'll talk about the effect of this. What we'll find might surprise some of you, and that will be the subject of the following slide and some calculation, as well as a link to our detailed calculation by numbers. Many times people talk about generalities, what will happen or not happen. The volume will flash, and that's bad news. The question we have to ask, how bad is it? Show me some numbers. Perhaps it's not so bad. The numbers, thermodynamics, proper engineering evaluation, step by step, will tell us if there is a problem or not and how to deal with it. So the following slides will go to that. And I hope you enjoy that. The PVA Pump Video Academy 8 and now Pump Video Academy number 9. You can see it on our website, which is pumpingmachinery.com, under a Pump Magazine section, which will lead you to article, I believe it's article 53 and 54, which in detail show that. Or we can also cover it, some of you coming to our pump school, the next one I believe coming up in January in Atlanta, 2-day pump school in which we'll cover this and many similar topics, including hands-on work on pumps. And until we see you again, keep on pumping. And I hope it was educational and you enjoyed it, I find it useful. I'll see you in the next module.
And so we discussed the general introduction to the lesson on Pump Video Academy number 9. And the Pump Video Academy number 8 was talking about the first portion of that presentation, when flashing is at the DA. And current one, PVA number 9, talks about piping portion of the flashing. So to see the articles themselves, what we need to do is go to a website, and once we're on the web, on pumpingmachinery.com, there are several buttons here to push. One of them is Pump School. Well, we'll need actually Pump Magazine online, this one, Pump Magazine. Then there's a series of buttons, Pump Articles, and then we'll scroll to article number 53. And article 53 is the part 1, 54 is part 2. And this is a description of the deaerator situation and some numbers. Article number 54 talks about our current situation and with numbers and calculations. So that's how you can get to the articles and read all the details. But coming back to the presentation slides, we have on our pump school, which is the tab below here, pumpingmachinery.com pump school. If you go to that side, there's several modules, and of course module number 8 is here. Number 9 will be positioned right here. That is probably how you got to this link to begin with. That number 9 will be positioned over here. We will start by, of course, referencing to this link to the Article 53, DA effect, and Article 54, pumping with a trapped hot water in the idling non-running pump. So let's go one more time. So we have a boiler feed pump and pumping to the boiler that gets heated and generates steam. Steam going through high pressure, low pressure steam turbines driving a generator. After the steam went through the turbines, it condenses in a condenser. Condensate pumps dumps it back to the deaerator. And then at the deaerator, the fluid stays in saturations, but when there is a upset, when the generator doesn't have load on it, then steam gets bypassed across into a condenser, and it gets interrupted, pegging steam not to go anymore to the deaerator. As a result of that, the pressure and the hot steam is not available. Cold condensate still goes in. That causes liquid to flash. And then the flash vapor gets trapped in, or can be trapped in, into the header, or suction header downcomer, into the pump, and of course, bad news to the pump. Well, that is, most of you probably know that the pump that is in cavitation is not a happy pump. And this diagram just explains as, in general, many auxiliaries, of course, holding tanks and bypass tanks. There's some other mitigating equipment that is installed, but simplified diagram of the cycle is shown on this slide. So, if you look at the pressure temperature tables on the left side here, and a diagram, in our example, at 302 degrees F, the fluid is in saturation at point A, just about to become vapor, but not quite vapor yet, at 69 psi absolute pressure. And then suddenly the pressure drops to 39 psi and 266 degrees Fahrenheit. And why does it suddenly drop? It suddenly drops because we just explained that steam is no longer coming. Cold water is cooling entire DA liquid. And as it's cooled, it's moving from A to B at the constant volume line. Because as we mentioned, the control volume of the entire DA and piping is constant. So as it's coming down the line, not to the right or to the left, but straight down the line, by the time it gets to 266 degrees, it'll be some X fraction, certain amount of vapor and certain amount of liquid. Mostly liquid, but some vapor. By mass, by the volume, it could be quite substantial. Or look at the table. 302 degrees, 69 psi, 266, 39 psi. The specific volume of liquid is relatively small. Specific volume of vapor is thousands of times greater, and that what makes it volume. That makes a volume of vapor substantial, and it goes to the suction of the pump. Well, when we have two pumps, and as we discussed earlier, when pump number 1 is shut off, let's say a couple of seconds before the pegging steam is interrupted to DA, let's say that at 302 degrees, initially, everything was at 302 degrees. At the previous slide here, 302 degrees, everything was at 302. And it remains at 302 and non-running pump. It's trapped there. Let's assume a perfect installation. DA is cooling to 266. The water is flowing to the pump number 2, and it's cooling. The pump P2, as well as P1, receive a constant head of 50 feet in this example, which is roughly 21 psi. So pressure to pump number 2 and to pump number 1 suction is 21 psi plus what's on top of the DA level, which was 39 psi. It went from 69 to 39. Well, the pressure reduction at the DA itself doesn't really affect the NPH ratio of either pump because it's in saturation. The pressure is subtracted from vapor pressure and the result is zero. But the standing head of 50 feet is fundamentally what the NPSA is for both pumps. However, at the reduced pressure and reduced temperature, the temperature in leg number 2 keeps on reducing. That's what saves the pump, and it keeps on running. The temperature at the pump number 1 leg, 100 feet of that, or 50 feet in this example, remains hot. The pressure is dropping. Therefore, it's no longer 50 feet of cold fluid, but 50 feet of the hotter fluid. The question is, how much hotter is this fluid? Well, we can go through a scenario of how the evolving bubbles, which obviously need to become vapors. They can't become vapors instantaneously because as the vapors gets created, it has to come over try to come over to the suction of the pump 2 and travel another 50 feet, also come onto the DA, and cause problems. The problem to that problem is that when the vapor bubbles reach the colder region, they'll have to be condensed. They will condense, as we talked at the video. And that condensing turns them back into liquid, and therefore no vapor would reach pump number 2. It will not enough time for these vapors to travel all this distance. They will condense into liquid sooner. So we can consider a situation of the extreme. What's the extreme? In the extreme, the entire energy of the hot 302 degrees of temperature has to translate itself into 266 degrees temperature. Well, actually, it will be happening in chunks, so in not quite as dramatic. But let's review a dramatic situation. So everything came to equilibrium. That means entire both legs will have to be now at average. Let's assume both legs are equal height and diameter. So 266 plus 302, 280 some degrees, will become both legs temperature. The question now is 288, too hot for the vapor pressure to start cavitation in pump number 2. Well, let's see. Consider the extreme example scenario which we just mentioned. 266 plus 302 is 284 degrees. Well, at 284 degrees, we'll have from a thermodynamic tables, the saturation pressure is 52 psi. Well, the pressure on top of the pump number 1 is 60 psi. Why? Let's go back and look again. Because it is 39 psi here, plus 21, that's our 60 psi. Well, we got 60 psi, and we need to reduce the pressure to 52 psi in order to come to saturation at 284 degrees temperature. So we are 8 psi greater, which is good news, 8 psi than the suction pressure, or 8 psi, the vapor pressure is 8 psi below the available 60 psi, 39 plus 21 static. That's good news. That means we're 8 psi, which is roughly 20 feet. If you take 8 and multiply by 2.31 over specific gravity, you get approximately 20 feet. So in summary, the main effect of the pump cavitation during the power transients is caused by the behavior in the DA, which we discussed last month, Article 53, and not likely adjacent piping being the problem. Obviously, each case is different, and the results could be different at other plants. Different sizes of piping, different DA designs, different bends and turns, speed of the pump, design of the pump, flow, insulation, and so forth. But overall, in the cases we just considered, doesn't seem likely that the intuitively speaking hot pipe and the idling pump causes a problem. Not a likely scenario. A likely scenario is more classical flashing of the DA during the transient, and the vapor that is in it reaching the pumps causes problem. Well, what's your experience? Many of you work in the power plants, perhaps some other situations quite as interesting and challenging, And if you have it, please let us know. And more on that, we'll talk in our upcoming pump school, which is in January of 2015. And these pump schools we repeat every couple of months. The link to get to us is given here. And the phone number and the emails on the screen. So I'll look forward to hearing from you. And until we meet again, as we say, keep on pumping.